Okay, sorry, my pen was not working, so that's why it was a little bit of delay. Uh, Today I'm going to continue with the linear transformation, and I'm going to describe a few theorems and the corresponding problems. So the first theorem that I'm going to discuss is the following. Let capital V and W be vector spaces, and let T is a function from V to W, and this function be linear function, is a linear transformation. Suppose it is given. Also, if beta is a set which contains some elements of the vector space denoted by V1, V2, Vn, and if beta is a basis for the vector space V, then RT, you know, RT is the range of T. The range of T will be actually spanned by, it will be spanned by the images of, it will be spanned by the image of these elements, TV1, TV2, ... TVN. Okay, so this is the theorem that I'm going to discuss right now. It's a very important theorem and it is actually used in so many problems. What this particular theorem is saying that you have got two vector spaces, one is V and another is W, okay, defined over the same field F, VF and WF, and you have considered one transformation T from V to W. Now in V, it's a many elements are there, infinitely many elements are there in V, but from these elements, you are choosing a set of elements. Say, for example, this is a subset of V, which is itself a vector space, and it contains the elements of V such as V1, V2, and Vn, like this. Okay. Now, if this set in green color, if this set, I'm considering this set to be beta, that means beta is containing some elements of the vector space, some n elements of the vector space. And not only this, beta is the basis for the vector space capital V. That means any element of the vector space V. So for example, if I choose an element from here, I'm choosing an element, say X from here, then this X can be represented as a linear combination of these elements V1, V2, Vn. Okay, so any element, X is arbitrary element, so any element you choose from vector space V, that can be expressed as a linear combination of the elements present in beta. This is the meaning of that. Now, if this is the case and V1, V2, Vn are linearly independent vectors, so if this is the case, then W must have a basis. So the elements of W must be spanned by something. So what is that span of W? The theorem says that under the transformation capital T, V1 is being taken to TV1, V2 is being taken to TV2, Vn is being taken to TVN. Now, the theorem is saying that if I contain these elements TV1, TV2, TVN inside a set, the set has not been named over here, then the theorem is saying that you know that RT basically a subset of the vector space W. Okay. Now, all these elements of RT, all the elements present in RT or range of T will be spanned by these images, TV1, TV2, and TVN. So we are going to prove this result first of all, and then we are going to implement this to a given problem. So how to prove this result? Let me show this to you first. We need to prove, we know that if I want to show that A is equal to B, A and B are two sets. And if I want to prove that A equals to B, then we need to show that, number one, we need to show that A is a subset of B, and number two, B is a subset of A. If these two simultaneously happen, then we say that A is equal to B. Now, here we have two sets. We can consider one set to be this capital set, this capital A to be RT, and this capital B to be this right hand side, this entire right hand side. We need to show that RT is equal to span of this set. So we have to first show that RT is the subset of this set, and this set is a subset of RT. If we can do this, we will be able to write that RT is the span of these elements. So we are going to do this. Now, just a minute. Now, you can, for the sake of the simplicity, we can name this set TV1, TV2, TVN. We can consider this set to be, we can also write it in this particular way. RT can be written also in this way, span of T of beta. But what does this mean? It means the same thing, because you see, beta is the set consisting of these elements V1, V2, ... Vn, and under the transformation, all these elements are going to have the image TV1, TV2, and TVN. Okay, now we can say, if this happens, we can say that we can name this set as T beta. That this entire set is being transformed to this particular set. This set is being transformed to set T beta. So basically, we need to show that RT is the subset of this span of T beta, and this span of T beta is the subset of RT. So let us start this problem. We need to show that RT is subset of span of T beta, and at the same time, span of T beta is subset of RT. Okay. Now, let us do the first case. This is case number 1. And this is case number 2. So let's start with the case number 1. How do we show that A is a subset of B? We choose an element from A. We consider an element from A. Let X belongs to A, and we simply show that X also belongs to B. If it happens, we say that A is a subset of B. And to show that B is a subset of A, we consider an element from B, and we simply show that it implies this element also belongs to A. X and Y are arbitrary. Then we say that, okay, A is a subset of B, B is a subset of A, and therefore A equals to B. In a similar manner, we are going to choose an element X from RT. Our objective is to show that RT is the subset of span of T beta. If X belongs to RT, this implies, by definition, it implies there exists an element V belonging to the vector space capital V such that T of V is equal to X. By definition of the mapping, if X belongs to RT, so there must exist an element V in the vector space capital V so that the image of V is equal to X. Since V is an element of the vector space capital V, and beta is, which is V containing the elements V1, V2, Vn, is a basis of capital V, then it is quite obvious that we can express this element V, as linear combination of these elements V1, V2, Vn. So we can express, so there exist some scalars, A1, A2, dot, 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 An in F, in the field, such that the element V, this element V can be expressed as linear combination of these elements A1 V1 plus A2 V2 plus An Vn. Okay. I think up to this point is everything is clear to you. Now I'm going to go to the next page. You just take a screenshot of that. And in the next page, I'm going to continue. Now, if V can be expressed as a linear combination of these elements, why V can be expressed as linear combination of these elements? Because V is an element of the vector space V, and beta containing these elements is the basis. So V can be expressed as a linear combination of these elements. Niladri, want to say something? You can unmute yourself.
স্যার একবার একটু বুঝিয়ে দেবেন স্যার, অনেক মানে আগে পড়েছিলেন ভুলে গেছি এটা।
Which part specifically mentioned? Which
Sir,
particular
basis
part? Basis. Basis, that what is the definition of basis? Basis means it is a set containing some elements of the vector space. The elements in the basis are all linearly independent vectors. That means none of the elements can be expressed as linear combination of other elements. All of them are independent of one another. Not only this, any element, any other arbitrary element of the any arbitrary element of the vector space can be expressed as linear combination of the basis elements. This is the definition of basis. If you forget the definition of basis, you can go through the book. It is written. Basis means it is a set containing, some elements of the vector space. These elements are linearly independent, and any arbitrary element of the vector space can be expressed as linear combination of these elements. This is the definition of basis. I described a situation where we considered the two-dimensional coordinate x, y, where we see that this coordinate xy can be expressed as a linear combination of these coordinates, x into 1, 0 and y into 0, 1. Even if you choose the point 1, 0 itself, 1 and 0 itself, then that can also be considered as a linear combination of these two elements. So you can simply write 1 into 1, 0 plus 0 into 0, 1. Any element of the vector space can be expressed as a linear combination of these elements 1 and 0 in R2 space. So this 1, 0 and 0, 1, this is the basis of R2, is basis of R2. We explained it in our previous class. Now, what is happening over here? We want to show that RT, that range of T is the subset, is equal to span of T beta. Is the meaning of the situation clear to you? What do we mean by this? Is it clear?
Yes, sir. Now it's
Now,
clear.
if you want to show that it is a subset of span of T beta, that means you need to show that RT is the subset of span of T beta, and span of T beta in turn is subset of RT. Now these two cases must simultaneously occur. We started with case 1. We considered an element X from RT, because you know this rule. We have to follow this rule. So we choose an element from RT. Now, since X is an element of RT, then by definition, there must exist an element V in the vector space capital V, whose image is X, and it is present in RT. So we must get an element V so that T of V is equal to X. Now we know that beta containing V1, V2, Vn is the basis of V. So by definition of basis, any element of V can be expressed as linear combination of these. Any element of the vector space V can be expressed as linear combination of this basis element. Small v is any element of the vector space. So obviously, V can also be expressed as a linear combination of these basis elements. So we choose some scalars. We know that there will exist some scalars A1, A2, An in the field, so that V can be expressed as A1, V1 plus A2, V2 plus ... plus An, Vn. Clear?
Yes, sir. Clear now.
Okay. Now,
Yes.
this implies that if I take the linear transformation on both sides, we will get T of A1 V1 plus A2 V2 plus ... plus An Vn. I'm taking the mapping on both the sides. We get T of V, and we know T of V is X. This can also be written as T of A1 V1 plus T of A2 V2 plus ... plus T of An Vn is equal to X. Why? Since T is linear. Since T is linear. Again, we can take the scalar outside. We can write A1 into T of V1 plus A2 into T of V2 plus ... plus An T of Vn, which is equal to X. Why? Since T is linear. T is linear. So what do we see from here? Carefully observe this particular part. What we have seen is that the element X, which was chosen from RT, we are capable of expressing the element X as a linear combination of these elements, TV1, TV2, and TVN. So obviously we can, from this particular part, we can immediately conclude that the element X is actually getting spanned by, because this is the definition of spanning set, it is getting spanned by the members TV1, TV2, ... TVN. Because we can express X as a linear combination of V1, TV1, TV2, TVN. So we'll definitely can say that X is being spanned by these members TV1, TV2, TVN. So obviously X is equal to this. Now, this particular thing, X, we shouldn't use the equality sign over here, because this is a set, span of T of TV1, TV2, TVN. This is a set actually. So after looking into this, we can say that X belongs to this set. Span is a set actually, spanning set. So in this spanning set, X is belonging. Okay. So we started with X, which was in RT, and we have we have seen that X is belonging to this particular set, which is nothing but span of T beta, because this set T beta is actually the set TV1, TVN, dot, 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 TV2, and TVN. So from this particular analysis, we come to this conclusion that the set RT is a subset of span of T beta. So one part is complete, that is, we can put it number 1. Now our next job is to consider the opposite. We want to show that span of T beta is actually subset of RT. So let us now discuss case 2. So we'll choose, now you just look at this, that to show that B is a subset of A, we have to take elements from B and we need to show that it belongs to A. So I missed one page actually. So it is written, this is my page 2, remember. So we choose an element Y from span of T beta now. We choose an element from span of T beta, that is Y belongs to span of this particular set, TV1, TV2, TVN. Okay. Now, if it is so, then there exist scalars. B1, B2, dot, 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 Bn in F such that Y can be expressed as the linear combination of these elements, B1 into TV1 plus B2 into TV2 plus dot, 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 plus Bn into TVN. Okay. And from this, it implies that we can write this thing as T of B1 into V1 plus T of B2 into V2 plus dot, 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 plus T of Bn into Vn. Why? Since T is linear. T is linear. This can also be written as Y is equal to T of B1 V1 plus B2 V2 plus dot, 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 plus Bn Vn. Why? Because T is linear. Understood? Any doubt in this particular logic or in any particular line, you can ask me now. Any doubt?
This is just the reverse case of the previous one, right?
Yeah, because if you need to show that A is equal to B, you need to prove A subset of B and B subset of A.
Yes, sir. Yes.
Okay, and A subset of B has already been proved when I proved RT is a subset of span of T beta. Now I am just taking the reverse. I'm considering span of T beta being subset of RT. That part I'm showing. So the way by which I proceeded, you just check the steps and tell me if you have any doubt regarding any step in any particular logic. If not, then we can continue. We can name Y to be T of some element V prime, where V prime is element of the vector space V. Why? Because I'm just naming these elements B1 V1 plus B2 V2 plus dot 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 plus Bn Vn as V prime. We can always do this because obviously this will be an element and this will belong to V. Why it will belong to V? Because what is the justification? Justification is that this element is actually being named to the linear combination of these elements V1, V2, Vn. And we know the linear combination of any elements of this type is actually a member of the vector space V. So we can write this because V1, V2 dot 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 Vn is equal to beta is a basis of V, is a basis of V. Okay, so therefore we named it as V prime. Now you see that I'm going to the next page. So we got y equals to t V prime, and we know that V1, V2, Vn is the basis of this vector space. So next we can write the following. Since beta is equal to V1, V2 dot 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 Vn is basis of capital V, so there exist element like V prime in V, and so there not so let me write as their linear combination, is a member of V, such that T V prime is equal to Y, and obviously this is nothing but an element which belongs to RT, which belongs to RT, and therefore we started with Y present in span of T beta, and we have come across that Y belongs to this RT. So therefore we can conclude that span of T beta is a subset of RT. The subset of RT. This is number 2. From 1 and 2, we can conclude that RT is equal to span of T beta. Proved. Now, what is the I mean, why this particular theorem is so important? It is because in the last class we actually discussed about the kernel of T, kernel of the linear transformation, and range of the linear transformation. You know, the kernel is a set which contains those elements of the vector space whose image is 0. Sometimes it becomes difficult to find the range of the linear transformation. So this particular theorem may help us to find the range very quickly. And remember one thing, that whether T beta is basis or not, that is not clearly mentioned, because I'm saying this, I don't know whether you have noticed it or not. I mentioned in the problem that beta is basis element of basis set of vector space V, but T beta, whether it is basis or not, I have not mentioned. Okay, so I'm only saying that span of T beta, spanning sets are not always basis. If the vectors of the spanning sets are linearly independent, then only it is basis. Span of T beta, this particular thing justifies that, okay, the elements of T beta can be taken as a linear combination to describe the element of RT. Okay, but whether T beta can be considered as a basis, that has not been clearly mentioned in this particular theorem. Okay, so so this part is not actually clear to us.
Sir,
Yes.
sir, you just said that the members of the spanning set have to be linearly independent to be called basis.
If the members of the spanning sets are linearly independent, then the spanning set will become a basis.
Okay.
Okay, beta is a basis. Beta spans a span of beta. Actually, span of beta is the vector space. Not only this, the members present in beta, they are also linearly independent. So beta is actually basis, it is declared. But here we see that span of T beta is equal to RT, but we do not know, we are not sure whether these elements present in T beta, whether these elements are Li or LD. LD means linearly dependent. We are not sure about it. Nothing is mentioned regarding this issue in the problem. So be very careful about this particular thing. When you are studying something, you have to be very careful that what each and every word present in the theorem or in the context are actually very important and contribute significant amount of knowledge in understanding the situation. So be very careful about this. Now we shall try to understand this theorem with respect to a given problem. Let us take a problem. Define linear transformation. Define linear transformation T colon P2R from M2 cross 2R by the formula T of Fx is equal to F1 minus F2 0 0 F0. This is the transformation which is given to us. Now we want to find RT. Our job is to find RT, and we are going to apply this particular theorem in this case. Suppose this transformation is given in this particular way. Now, can you tell me what is this set P2R? What is the meaning of this set?
A polynomial of degree 2.
Is it? Is it? You are not specific about the set P2R. Say it specifically.
A
We have-
polynomial of degree 2 with real coefficients.
No, no,
Whose field is
no, no, no. What are you saying? I'm not understanding anything. What is
the
this set?
polynomial of degree.
First of all, you tell me what is this set?
The polynomial of degree n defined on scalar field F.
Polynomial of degree n? No. Anybody? It is set of all polynomials. Now fill in the blank. Fill in the blank. It is a set of
Not
all
degree,
polynomial
degree.
having degree.
Having degree n.
No, not you are not specific. Having degree. Having degree.
In such that n belongs
Less
to
than
a
or equal to n.
scalar field.
Having degree less than or equal to n.
Okay, sir. Okay, sir.
You are saying it is a polynomial of degree n only. No, it is not a polynomial of degree n. It is a polynomial of degree less than or equal to n. And this PNF is actually a subset of
Sir,
PF.
that is implied, sir. If the
No, it is not
I
implied.
mean the coefficients of
When
the
you
higher
say
order,
no,
if
it
the
is not.
coefficient of the higher order is 0, then
It is not implied when you say that it contains only the polynomial of degree n. That means only terms like x to the power n, any polynomial of this. If you say P2R is the polynomial of degree 2, that means polynomials like x square plus twice x square plus 1, this type of thing will present over there. It doesn't mean that x plus 1 will be present over there. If somebody asks that whether x plus 1 is present in P2R, you will say that no. I said that it is a polynomial of degree 2. But if you say it is a polynomial of degree less than or equal to 2, then you will say that, okay, x to the power 0 terms, polynomial having degree 0, 1, 2, everything will be present in P2R. The two statements are totally different from one another. So P2R is the set of, you just be careful about the sentences. It's a set of polynomials having degree. Forcefully, you cannot justify anything less than or equal to 2, defined over the set of real numbers. Defined over the set of real numbers R. R is the set of real number. When we say that it is defined over the set of real numbers R, what do we actually mean by that? Suppose we are considering the polynomials having degree less than or equal to 2, and we are saying that it is defined over the set of real numbers R. What do we mean by that? What is the meaning of this? Tell me. Defined over the set of real numbers are. What do you mean by that?
the coefficients belong to R.
Exactly. It means that the coefficients of the polynomial, coefficients of these polynomials have been chosen from R. Have been chosen from R. Real coefficients. Okay, that means it is defined on R. Now tell me, what is M2 cross 2?
So set of square matrices of
Of
order 2
2.
defined on R.
Defined over
Order
R.
2.
Yes, okay. Now, can you tell me what is the basis of P2R? What is the basis of P2R? Which set is the basis of P2R? I think I will be able to continue in the next session, because this session is going to end. Less than 1 minute is required, but you think and tell me in the next session that what is the basis of P2R? Any idea?